Welcome to Lecture 33, whose subject is electric circuits. These assemblages of electronic components and devices are ubiquitous. They're in all our electronics, they're in our cars, they're in our appliances, our houses are electric circuits, the entire power grid is an electric circuit. We're going to look at electric circuits in this lecture and see how to analyze and understand how simple circuits work. So let's begin just looking at a circuit. Here's a photograph. This is actually a circuit board from a piece of electronic equipment. You see a number of interconnected electronic devices. The big black thing in the foreground with all the legs is an integrated circuit that probably has millions of electronic components in it. The small cylinders in the foreground are resistors, devices engineered to have specific resistance. And in the background, you see some disc-shaped capacitors, and behind them, an electrolytic capacitor. So what is an electric circuit? It's an interconnected network of components, resistors, capacitors, all kinds of other things we aren't even going to talk about in this course, and usually, almost always, with some kind of source of electrical energy. And I want to spend the next few minutes talking about that source of electrical energy that we have in circuits. So how do we energize circuits? We do it with something called a EMF. Now, this is an obscure term. It's based in history. It stands for electromotive force, which is actually a very misleading term. So we just call it an EMF. And an EMF is a source of electrical energy that maintains a constant potential difference across two electrical terminals. So examples, batteries. We've talked about batteries before. They're sources of EMF. So are electric generators. Here's some generators from a hydroelectric station. So are power supplies, which are devices I might plug into the wall. I had one in the recent lectures when I was charging up a capacitor, and I'll be using power supplies more. Power supplies we plug in and they produce a given voltage, fixed voltage across their two terminals. Photovoltaic cells that we use to generate electricity from sunlight are EMFs, sources of EMF. Fuel cells that we may use someday to power hydrogen-fueled cars. And finally, thermoelectric devices which convert heat relatively inefficiently into electricity. Those are all examples of EMFs, sources of electrical energy that can energize circuits. So let's look at some circuits. Here's the simplest possible circuit you could imagine. A source of EMF, a battery in this case, and some kind of electrical load, in this case, a light bulb. What happens in this circuit? Well, charge, I've indicated charge at the positive terminal, flows through that circuit and goes from the battery's positive terminal through wires, through the external load, and comes back to the negative terminal. Now, be careful. In fact, we know that the charge carriers in most common circuits, because they involve metallic wires, are in fact electrons, and the electrons are actually going the other way. They're coming out of the negative terminal, going the other way and into the positive terminal. That's what's actually happening. But it doesn't matter. The current is still in the same direction from positive to negative, and so I'm going to talk about circuits as though positive charge is flowing. It doesn't matter. It really makes no difference whether it's positive charge moving from the positive to the negative or negative charge moving from the negative to the positive. So charge flows from the positive terminal through the wires to the external load, through the external load, back to the negative terminal. What happens when it gets to the negative terminal? Well, if you think about the battery is maintaining positive charge on its positive terminal and negative charge on its negative terminal. It's doing that as a result of chemical reactions that occur inside the battery. So here comes this positive charge back to the negative terminal, and it experiences an electric field inside the battery which points downward from positive to negative. So how does it get back to the positive terminal? Well, that's the trick that the battery knows how to do. Chemical reactions inside the battery do work on that charge, and they lift it, like lifting a weight against gravity, against the battery's internal electric field, and they deliver it back to the positive charge, positive terminal, and of course they do so at the expense of their internal chemical energy, which is why the battery runs down and either has to be discarded or, if it's rechargeable, can be recharged. Let me give you a demonstration of a rather simple mechanical system that illustrates what in fact happens inside a battery. So over here I have a rather silly toy in which there's some penguins. And the penguins represent electric charge, and inside here there's a motor that is going to run a kind of escalator that's going to raise those penguins up. That's like the chemical action inside the battery, lifting positive charge against the battery's internal electric field. And then the penguins are going to ride down this kind of slide, and that's like the external circuit. They're going to go through the external circuit, they're going to come to the bottom, and then that internal source of energy is going to again lift them. So here go the playful penguins, being lifted by that energy. They reach the positive terminal, they slide down through the external circuit, return to the negative terminal, where the internal chemical reactions again lift them against the internal electric field, in this case lifting them against the field of Earth's gravity, and away they go. So there's a very simple mechanical analog of what goes on inside a battery. Okay, so now we understand how a circuit is energized by some kind of source of energy. Let's look a little bit more closely at energy in electric circuits. First of all, we have a quantitative measure of energy, and that's the work per unit charge that the battery does on these charges, and it's therefore the work per unit charge or the energy that the battery delivers to the external circuit. But energy, we know, is conserved. So let's look at conservation of energy in an electrical circuit. And here's a slightly more complicated circuit consisting of a single battery and now two loads, two light bulbs, and they're connected one after the other in what's called a series combination. More on that in a minute. And here's what happens. Charge flows from the positive terminal through the load and back around to the negative terminal, and then again it's boosted inside the battery. So whatever energy it gains from the battery, it gives up in the load. And again, in circuits, when we talk about energy in the electrical context, we usually talk about voltages or potential differences, energy per unit charge. And so here's what happens. The battery has some voltage, V battery. I buy the battery. It's a 6-volt battery, a 9-volt battery, a 1.5-volt battery, whatever. The battery is supposed to maintain that voltage across its terminals. There's some voltage across the first load and some voltage across the second load, and those voltages represent the energy per unit charge that's lost as charge moves through those loads. In this case, they're light bulbs, and so that energy is converted into visible light and heat in the light bulb. But here's what has to be true in order for this system to conserve energy. Whatever energy is given to the charges by the battery has got to be given up to the load. And so the voltages across the two loads sum up to the battery voltage. So in a simple circuit like this, we can conclude that the sum of the two voltages across the load, or 3 or 4 or however many there were, has to sum to the battery voltage. And that's going to be a key factor in now our understanding of how to analyze electric circuits. So we're going to spend the next few minutes looking at slightly more complicated electric circuits and trying to understand how we analyze them. So just to get started, we write circuits, we draw them as little diagrams with these circuit symbols, and I've illustrated here some very common circuit symbols. We'll see the sort of diagonal squiggly line thing there on the left is a resistor. We have capacitors as a pair of parallel plates. We have batteries, and I've shown some meters, voltmeters, ammeter, and a switch there also. But I'll be stressing mostly resistors, capacitors, and batteries in the circuits I'll be talking about today. So, two ways to connect electrical components. One way is to connect them in series. If components are in series, the only place current can go after it moves through one component is through the next component. So on the left here, we see a battery and two resistors connected in series. And because the only place charge can go after it leaves the battery is through the first resistor and then through the second resistor, the flow of current in a steady state has to be the same everywhere. So in a series circuit, the current is the same in all elements of the series circuit. On the right, we have a parallel circuit. Here we've got two resistors, and they're both connected across the battery. Well, since they're both connected across the battery, and the battery maintains a fixed voltage or potential difference across its terminals, they get the same voltage across the two circuit elements, across the two resistors. But here's what else happens. There are currents, got the same voltage, there are currents flowing in this circuit. Two currents through the two resistors have to add up to the current that's coming from the battery, or else charge would not be conserved. And we're going to use these facts now to analyze more complex circuits involving series and parallel resistors. So let's get started. Here's our big monitor on which we like to do quantitative things, and we'll start by looking at series resistors. So here I've got the same series resistor circuit I just showed you. I've got a battery with some voltage VB. There's the battery symbol. The long bar in the battery symbol is the positive terminal of the battery. I've got resistor R1 and resistor R2, and I'd like to analyze this circuit. That means I'd like to understand the currents that are flowing in the two resistors and the voltages that appear across the two resistors. Well, we know by energy conservation, as we saw a few minutes ago, that the sum of the voltages across the two resistors have to add up to the battery voltage. If that weren't true, energy wouldn't be conserved as I went around this circuit. Whatever energy the charges gain from the battery, they lose in moving through those resistors. So there's the statement of energy conservation. We also know, as I just showed you, that when we have a series resistors, we have to have the same current flowing through each of them, because once charge flows out of the battery through resistor R1, there's no place for it to go but through resistor R2, and unless charge is beginning to accumulate here, which can't happen in a steady state, or be depleted here, we've got to have the same current flowing through each. It's like hooking a couple garden hoses together. However much water is flowing through the first one has got to flow through the second one because there's no place else to go. So that current I is the same. Now we understand Ohm's law also. Ohm's law says that voltage is the product of current and resistance. That's one of the three ways of writing Ohm's law algebraically. So we know that the voltage across the first resistor, V1, is that current, I, and I haven't labeled the current with any subscript because it's the same for both resistors. It's I, R1, and V2 is similarly I, R2. Same current through both resistors. Now we're going to take these two statements that tell us what those voltages are in terms of the current, which we don't yet know, and we're going to use them in that statement of energy conservation. So V1, which is IR1, plus V2, which is IR2, adds up to V battery. Do a little algebra on that, factor the I out of both these terms, and divide by the sum R1 plus R2, and we've got V battery over R1 plus R2 is the current. So now we know the current in this circuit. And we can conclude that this looks just like Ohm's law, I equals V over R, except that instead of R, we've got the sum R1 and R2. So we conclude that the series resistance here, the combination of these two resistors, adds up to a series resistance, which is simply the sum of the two resistances. Series resistors add, and it's a simple matter to extend this argument to multiple resistors in series. They are equivalent to a single resistor whose resistance is their sum. So that's series resistors. That's one of the two simple combinations I introduced a few minutes ago. Let's look a little further at series resistors. Series resistors, same circuit we just had, have the property that they take the battery voltage, or whatever the source is, and divide its voltage into two parts. And those two parts turn out to divide in proportion to the two resistors. And I want to demonstrate that here. So here's our result from last time. We had V1 is IR1, V2 is IR2, and I, we now know, is V battery over R1 plus R2, the series combination. And what I'm going to do now is ask, what are these individual voltages V1 and V2? Well, they're IR1 and IR2, but now I've got an expression for I. So V1 is I, that whole thing, times R1, and that whole thing is VB over R1 plus R2 times R1, and I've rearranged it a little bit algebraically to lump the terms involving the resistors all together, and they're multiplying the battery voltage. And I've done the same thing for V2. It's IR2. I've lumped the terms involving the resistors together and multiplied it by the battery voltage. This quantity that you see here, R1 over R1 plus R2 for V1, and R2 over R1 plus R2 for V2 is called the voltage divider fraction. This circuit is a voltage divider. It divides the voltage from the battery into two pieces, not necessarily equal. They're weighted by how big each resistor is. The bigger the resistor has the bigger voltage across it. There's some special cases that are worth looking at. If R1 and R2 were equal, for example, V1 would be equal to V2. R1 would be equal to R2. These numbers would be the same. These would add up to twice either resistance, and this fraction would be a half, and so we'd divide the voltage in half. If R1 is much, much bigger than R2, then most of the voltage is going to be dropped across R1, and very little of it across R2, and so V2 is going to be very small. This fraction is going to be small, and V2 is going to be very small compared with the battery voltage. And finally, if R1 is relatively small compared to R2, then this fraction will be relatively small. We won't have much voltage across V1, across R1, and most of the voltage will drop across R2, and that means R2 voltage, V2, will be essentially the battery voltage. That's going to be important in thinking about how real batteries behave. So I want to take this result and I want to move right on to talk a little bit about batteries as examples of this. So let's look at real batteries. Here's an ideal battery. An ideal battery is a device, you go buy it at the store, you buy a 1.5 volt battery and it says, I'm going to maintain 1.5 volts across my terminals no matter what. No matter how much current I draw in particular. An ideal battery is impossible. If we had one, it would be the solution to all our energy problems because it could supply infinite energy, because it could supply infinite current, and current times voltage is power, we could get infinite power. That's not possible. A real battery looks something like this. It looks like an ideal battery with a resistor in series with it. Now, that's not how batteries are made. They don't take ideal batteries at the battery company and stick resistors. The resistor represents the slowness of the chemical reactions going on inside the battery. The resistance represents actual resistances of the materials making up the battery. It represents a lot of different processes that make the battery less than ideal. So when we buy a battery, we buy what's inside that red box, and all we have access to are the two terminals. Then we connect a load, something we want to supply energy to, across the battery, and we have exactly that series voltage divider circuit we had before. So there's the voltage divider, and we're talking about what was V2 in our voltage divider analysis. Well, in this case, that becomes the voltage across the load, and that becomes our load over what was R1 before, now is our internal, and our load. And that fraction of VB is what we'll get across the load resistor. Let's look at special cases. If the internal resistance is much, much less than the load resistance, then essentially the load sees the battery voltage. That's the way we normally like to use batteries and sources of electrical energy. We like to have a load resistance whose resistance is large compared to the internal resistance, or equivalently, we like the internal resistance to be small compared with the load resistance. And then the battery is behaving normally. If, on the other hand, we have a very low load resistance, then the battery will simply not supply its full rated voltage across the load. In fact, there will be much less, and the energy will be going to heating up the internal resistance. That's not what, in fact, we want to do. So let's just take a second and look at some batteries. Over here, I have some batteries that we've worked with before. Here's our car battery. Here are two 1.5 volt batteries, a AAA and a D battery. What's different about the two batteries? Why does this one cost more? Why does this one last longer? Why can this one supply a more powerful flashlight with energy? Because it's got a lower internal resistance. They're both 1.5 volt batteries, but what's different is their internal resistance is different, and this one's internal resistance is lower than that one. The reason the car battery is so big and massive is because it has to supply 100 amps or so to run the starter motor of the car. And that takes a very, very, very low internal resistance, because if you had any significant resistance, if you had 1 ohm, you'd try to drop 100 volts across that. You couldn't do that because the internal battery is only 12 volts. But you get the idea. The internal resistance of the battery has to be a tiny, tiny fraction of an ohm in order to supply those very huge currents. So this whole idea of internal resistance is what distinguishes real batteries from ideal ones. And if you want to use a battery and make it work well, you use it in such a way that the internal resistance is low compared to the load you're connecting across it. Okay, that all came from series circuits. Let's now go back and look at parallel circuits. So here are parallel resistors. They have the same voltage across them because they're both connected across the battery. Charge has to be conserved in this case. So here's the battery delivering a current I, and here goes a current I1 through resistor R1. They're not in series, so they don't have to have the same current. Here goes a current I2 through resistor R2, and those two currents have to add up to I, or otherwise charge would not be conserved. We know Ohm's law again. In this case, we know that I1 is the battery voltage, which is across resistor R1 as well as across resistor R2 over R1. I2 is V battery over R2, so add those two up. I1 plus I2 has to be I. V battery over R1 plus V battery over R2 is the current I from the battery. Do a little algebra, factor out the V battery from those, and write I like this. And that looks like Ohm's law, except the thing multiplying VB looks like 1 over some resistance, and it's 1 over the parallel combination. So 1 over the parallel combination is 1 over R1 plus 1 over R2, and you could do some algebra to get an expression for R parallel itself, but it's sort of nicer to write it that way because we conclude that parallel resistors add reciprocally. So now we understand parallel resistors, And now we're ready to look at more complicated circuits. So let's take a look. Here's an example of a more complicated circuit. This circuit has 4 resistors and, in this case, a 12-volt battery. And I'm not going to go through the analysis in detail, but here's how we would do it. We first identify series and parallel combinations. We reduce that to a simpler circuit. We repeat that, we repeat that, we repeat that till we can solve for something. So there's a parallel combination of resistors. I can figure out the parallel resistances I just showed you. And now I have a circuit that's simpler. It consists of 3 resistors. One of them is that parallel combination. There it is. Now I identify 3 resistors in series. I know how to calculate series resistances. They simply add. So now I have a single resistor, and now I can calculate the current through that resistor. And then I can go backwards and figure out anything else I want to find out about the circuit. So that's one way to analyze complicated circuits. There are even more complicated circuits. Here are 2 examples. These circuits cannot be analyzed with series parallel combinations. You look at them, you can't find any series parallel combinations. The first one's got this complicated structure to it. The second one has a bunch of different batteries. By the way, the lower circuit is, in fact, a very important circuit in biology. It's the so-called Hodgkin-Huxley model for the cell membrane. And it won its discoverers the Nobel Prize. And it describes the electricity flows that happen in a biological cell membrane. There are no series or parallel combinations in these, so what we do is write conservation of energy for each circuit loop in one of these circuits, and conservation of charge for each node, each point where current can split and go different ways, and we solve multiple equations and multiple unknowns. And I'm not going to do any more with that here. If you became an electrical engineer, you would take entire semesters of circuit analysis, and you'd understand the mathematics of how to deal with such circuits. So that is how we handle really complex circuits. Well, I want to end by looking at one more example of a component that we can put in circuits, and that's capacitors. We've already seen capacitors. We understand how capacitors work. What capacitors do in circuits, though, because you have to flow charge onto a capacitor in order to charge it up, in order to change its voltage, because charge and voltage, remember, are proportional in a capacitor, capacitors fundamentally introduce a time delay into a circuit. So that's what capacitors do. They affect timing in circuits, and for that reason they're used in all kinds of applications. When you adjust tone controls on an old-fashioned stereo system, or maybe the balance controls, the equalizers on a more modern one, you're typically adjusting the behavior of capacitors. You may or may not be adjusting capacitors. You probably aren't. But you're adjusting the way certain capacitors in there behave. Capacitors smooth out alternating voltages to make them steady and smooth. They do that because they introduce time delays. We use capacitors where we need time delays. Simple timing circuits can be built using capacitors. Let's see how that would work. Here is a simple circuit that consists of a battery with its voltage VB, a switch, a resistor, and a capacitor. I'm going to close the switch. The capacitor is going to be initially uncharged, and I'm going to ask what happens. So the capacitor is initially uncharged. Time t equals 0. I close the switch. The voltage across the capacitor, V sub c, was initially 0. And so that means the voltage across the resistor, once that switch closed, had to be the battery voltage, because those two voltages, R and C, VR and VC, have to add up to the battery voltage, as we've seen. So there's current flowing through that resistor, because if there's a voltage across the resistor, there's current. In fact, we can calculate that current. At first, it's V battery over R, and it delivers charge to the capacitor. So the capacitor charge increases, and so therefore does its voltage, because charge and voltage are proportional on a capacitor, as we saw from the definition of capacitance. So the capacitor voltage increases. That means the resistor voltage decreases, because the sum of those two is the battery voltage. That means the current decreases. That means the rate at which charge goes onto the capacitor decreases. And that means the rate at which the capacitor voltage is increasing decreases. And that process just keeps occurring. And the result is an ever-slowing rise in the voltage across the capacitor. It happens to occur with a characteristic time given by the product of resistance and capacitance. And I'm not going to do this here, but if you take the SI units for resistance and capacitance, reduce them to their fundamentals, you'll find they come out in seconds. And that describes the characteristic time for changes to occur in a circuit like that. And here's what we expect from this picture, the voltage across the capacitor to look like as a function of time. It starts charging rapidly, but it slows down and slows down and slows down as the rate of current flowing through the resistor decreases and the rate of voltage buildup across the capacitor therefore slows. And a capacitor gets to about 2/3 of its final charge in about one of these time constants RC. So I've shown you out here to 4 of these time constants RC, and by then it's almost fully charged to the battery voltage. Well, let's take a look at how this works in the real world. Let's pause here and do a demonstration on our big screen monitor of a capacitor circuit charging. Okay, so here we are ready to demonstrate this proposition that capacitors act as slowing down agents in circuits. They introduce delays. I have here the same capacitor that I used in a previous lecture to zap a screwdriver. I stored a lot of energy in it. I'm not going to store as much energy in it this time. The capacitor is connected in series with a resistor. It's a rather heavy-duty resistor because of the big amounts of energy I was storing in it before. The resistor happens to be about 250 ohms. The capacitor is about 1/100th of a farad. Remember that that product of resistance and capacitance gives a characteristic time associated with that delay. So if I multiply 250 ohms by 0.01 farads, I get about 2.5 seconds for the characteristic time for voltages to change in this particular circuit with this capacitor and this resistor. And I have the circuit hooked up to a 6-volt battery, which will be my source of power to energize the circuit. And I also have it connected up to this oscilloscope, which is, again, a voltmeter, basically, that records voltages as functions of time. And the beauty of the oscilloscope is it can record very short times down to billionths of seconds, or very long time, up to seconds to minutes. And we're going to use it for relatively long times because we have a relatively long time delay of several seconds. But I want to emphasize again, capacitors and resistance come in an enormous range of values. So I could have built a similar circuit where that characteristic time was a billionth of a second. And I could have done exactly the same thing I'm doing here. It just would have happened very, very fast. We still could have seen it with this oscilloscope if we did the experiment repetitively and looked at it over and over again. But we're going to do it on a time scale that we can actually look at. And for you to see it better, we have the oscilloscope hooked through a wire to our big screen monitor, so you'll be able to see what's happening on the screen of the oscilloscope also on the big screen monitor. So what I'm going to do is begin the experiment by, first I'm going to short circuit the capacitor. Like I did with the screwdriver before, I want to make sure there's no residual charge in it. In fact, there is some residual charge in it because I've had it connected up to the battery. And so I'm going to start the oscilloscope going. I'm going to discharge the capacitor, and then the capacitor, I'm going to take the short circuit off the capacitor, and I'm going to let the capacitor start to charge, and we'll see that characteristic curve showing the rise, the slow rise of the voltage as charge begins to build up on the capacitor. So here we go. And there we go. The curve is rising with an ever-slowing rate, rising with about that 2.5 second time scale. And here we go, going toward that level of 6 volts. And let's make sure we've got what we think we have. I'll stop the oscilloscope there. We can talk about what we've got. In the upper left corner of the screen, it says 1.00 volts, and that's telling me that each of these divisions, vertical divisions on the screen, is 1 volt. So we started out at 0 volts, 1, 2, 3, 4, 5, and 6. And that battery, the one we measured in an earlier lecture, it was about 6.4 volts, and that's just about what we're getting to. So the voltage is rising from 0 at an ever-slowing rate and gradually leveling off at 6 volts, or a little bit more for that battery. The other important parameter on the oscilloscope screen is this number, 2.0 seconds. That describes how long it takes to traverse one horizontal division on here. So 2 seconds, I calculated that the characteristic time for this combination of resistance and capacitance was 2.5 seconds, and it ought to take about 2.5 seconds then for it to get up to about 2/3 of its full value. So we started right here, and one full division is about over here, and indeed we're up to about 2/3 of the final voltage we're going to get to. So we've confirmed not only qualitatively but also quantitatively our description of what was going on in that RC circuit. And let me just point out there's an awful lot of jaggly noise on here, which has been giving our oscilloscope some trouble. That's caused by some electrical equipment operating somewhere in the building that is introducing stray electric fields into the situation. Okay, so let's take a look now at what we've seen in lecture number 33. And let's summarize it. We've looked at electric circuits. They generally include interconnected electrical components and a source of energy. The components can be connected in series or parallel. We've shown that series resistors add, parallel resistors add reciprocally. Complex circuits require more complicated analysis, and that capacitors introduce time delays into circuits. And let me end with just a very quick challenge for you if you'd like to do a little more math. Here's a complex circuit. I had a slide that talked about analyzing complex circuits. I went through part of the analysis for you. I'd like you now to find the current through the 2 ohm resistor in that slide, Analyzing Complex Circuits. Let's look at the solution. The current through the 5.33 ohm combination resistance in that figure, 12 volts across 5.33 ohms. Ohm's law gives us 2¼ amps. That's the current through the whole series combination in the middle figure, including the 1.33 ohm resistance. So V across that 1.33 ohm resistance, applying Ohm's law again, comes out to be 3 volts. And that's the voltage across the parallel combination in the first figure, and so it's the voltage across the 2 ohm resistor. So that gives us I2, 3 volts across 2 ohms, 1½ amps, and if you got that, you're on your way to being an electrical engineer.